So we're going to go over the coding solution to this problem together. So this is going to be the dynamic programming problem where we try to solve in the forms of smaller problems. We're not going to use recursive in this situation because, as I've explained, we're going to just loop backwards. And as we loop backwards, we're going to analyze the data and store the data in a way such that when we want to access the first element, we can quickly see, we'll have that basically will solve the solution for the entire array and then go through it. So when we first look at this problem, knowing that we want to go backwards, we want to store some sort of array or some sort of way of storing what the solution is for each index in this num. So when I'm at 4, I know the solution is always going to be true. When I'm at 1, what I'm going to do is I'm going to check. I'm going to see, okay, I can go one jump. Where does one jump take me? And if it takes me to 4, that's good. If I go down to here and I look at 3, when I look at 3 and I try to look at the maximum place I can go 4, I can go to the next one, I can go to the next one. So we know that once we get to this position, we can mark that at this position we always can hit the end of the array. At this position we always can hit the end of the array. At this position we can always hit the end of the array. So then when we look at the first element, we just have to look um, one jump or two jumps or three jumps. And we can start by two jumps and go back to one jump. So first thing is let's store for every element in here as we're searching backwards. Let's store, so you can see here, so let's store the result. Okay, so here we're just going to have a basic array, and this will be our memo because this is a form of memoization where we're storing the result of a smaller problem to access it later. So we're going to mimic the size of this array. So, and we're just going to say nums.length. And here we have the size. We have a new array with the same size. So in this new array, what we can do is we can go ahead beforehand and fill the array saying that each position is false, but doesn't really matter. One, we're going to store values in this array. So 1 is going to represent good, and 0 is going to represent bad. So we know the last element is good because it's our final element, so we consider it good. Consider that if we are able to get to this state, we can always get to the next one. That's what you can imagine it as, rather than being the end of the array. It's just the end of an array for us. Um, so we're going to set memo of memo.length. We're going to set it to good. Now we have to start solving this problem backwards. So we're gonna solve the problem by iterating backwards. So remember, it's important to know how to, you know, even though even though this is not a efficient solution, it's important to know how to quickly set one up so that you can start to optimize it. So know how to do quickly things like reversing backwards in an array. So here it's a simple loop. We're going to do nums.length minus 2 y2 because we actually already know from this position. So we're going to start here. And the way to do that is to just subtract 2. And we always want n to be greater than or equal to 0. And n is going to be decreased each time this loop is ran. So now that we're reverse iterating, we're on the element 1. And at this element, what we need to find out is um, how far can we go? So there's also a scenario where this is 10 and we can go out of the array. So we can either go out of the array, we can go to the end of the array, or we can end up less than the array as our maximum jump. So this is our maximum jump. So integer max jump is going to equal to, so what information do we need? Well, if we go past the array, you're basically here. If you go below, that's fine. So we're going to use a minimum function because we're going to find out what's the furthest we can go and compare that with this element, this index. And if it's past there, we can just do this position. So you also could do a, if element is greater, if position of the element is greater than last position, then set the answer to, the last position. So we can easily just do this with a math.min, and this is something to get used to using and thinking about how to avoid doing additional code logic and use an existing function. So we're going to do the math.min of what's our max jump. So let's get this value first. Nums I plus, we can make one jump from position 0, 1, 2, 3, or n, and we want to make that the minimum of that and the last n. Okay, so here we have the minimum of the furthest place we can go. In this case, this answer will be 4. In here, the answer would be 4. If this was 5, this would be 4. If this was 0, it would be just there. So we have our max jump. Now what we have to do is, so we know here what the maximum jump is, meaning what's the maximum position we can hit. What we now need to do is we have to record at the place we're at. We have to record whether we're here, 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 if our position is good, meaning at the position we're at, can we reach the end? And when you look at it from the perspective of being at this element, your mind will start to think, okay, I'm next to the last one. But you don't want to think that. You want to think, uh, if I'm at this one, I'm at 1, and I know the maximum I can go is 1. Let me go check that one. Let me go check to see if it's been solved, because in this position it's obvious, but if I'm down here and I need to record, okay, at 2, the max I can go is to 3 or to 1. So in order to find out if I'm good at this position, I need to go check if I'm good at the other positions. So I have to actually, at this position, search forwards. I have to actually search forwards and go check. And then it's like, how far do you search? Well, I only can hit these 2 elements, so I'm only going to search up until these elements. I'll go to 3 and I'll check, am I good? I am actually good there. I go to 1 and I check, but I'm not going to go here because I could never get to this position from here. I only can get to these positions. So in order to record now, if I'm good at this position, I have to have an algorithm that looks forward and checks. So meaning that for integer j equals I plus 1, we're going to start forward. J is less than, what is it, max jump? J is less than or equal to max jump, and we go forward. Now, while we're going forward, we check if memo of j, meaning that we're checking now at 3. If 3 is good, 1. If 3 is good, 2 is good, right? If 3 is good, we are only looking in where we can hit, which is this part. 3 is good, so I'm going to mark 2 as good. I'm going to mark I, the position we're at, as good. Also, I don't need to loop forward, so I already found out I'm good. I already know I can hit the end because I looked at the ones I can hit, and those can hit. So we'll just break the loop. We'll break the loop. We're good here. Now at the very end, what we're going to do is we're just going to check. Let's get the first element. So let's get memo, and let's get the first element and see is it equal to 1. This will return if memo is good or not. Let's run this code. Nums of I math.min nums of I plus I here. And forgot to put the comma. Oh, I used a different variable. That's my mistake. And I have insert on. Should have used I, but that's fine. So we are able to submit. We're getting around 30%, around 29%.